Hello, this is Eric from UNC Charlotte. Imagine the situation. You have a piece of code you want to execute on a parallel platform, so you extracted the dependencies, you computed the metrics, and it turned out there is no parallelism in the code. What now? Do you forget about it? In some cases, there is nothing you can do. But before we give up, we should first try to see if we can redesign the code to get more parallelism. Maybe we can rewrite the code differently and change how the tasks and dependencies are defined. The bad news is there is no cookie-cutter approach that will work all the time. Really, the approach is to write the code or algorithm differently and see if that version is parallel. With experience, we will quickly be able to tell which approach is going to work and which doesn't. It often involves answering what-if questions about the code, or thinking of a different algorithm to compute the same thing. A classic problem we would have comes from a code like this one. For all values of I, we call a function f and reduce the value to some index. This code creates two chains of tasks, and if the call to function f is expensive, then this would have a high critical path. However, one can notice that the loop can be split in two loops to pre-compute all the values of f first. And if we are in a case where all the calls to f can be performed in parallel, then we would have exposed new parallelism in the application. Now all the calls to f can happen at the same time. The reduction still needs to happen in a long chain, but if most of the calculation are carried by the call to f, then the critical path would be small. Another typical example comes from code that were written with variables defined at a large scope for no real purpose. Here we have a matrix vector multiplication code, and all tasks of loop I and j will write on the sum variable. Because that variable is shared by all tasks, the graph of tasks is the long chain, and the work and critical path are both in theta of n squared. A simple solution is to remove the dependency to the sum variable, either by bringing it to the scope of the I loop, or by getting rid of it by writing directly on y of I. This causes the graph to become more parallel as it is now a collection of chains. The work remains in theta of n squared, but the critical path is now in theta of n. Maybe we have a case where all the tasks are writing to the same variable, causing the graph to be a long chain of tasks. If we know how much parallelism we are trying to achieve, we could try to introduce one variable per processor that we are trying to use. We can then rewrite the algorithm to use the different variable based on which task it is in. By doing that, we extract a bunch of chains of tasks. Now, there was probably a good reason the code was written using a single variable, and so probably that modification will lead to a code that is incorrect. But in many cases, the code is going to be wrong in a way that is easy to fix afterward. If the dependencies are caused by more complex variable accesses, it can be hard to introduce more variables, but targeting a particular number of processors can still be helpful. An idea is to think of the execution as a continuous piece of work, and just to chop it in p chunks. Maybe we can rewrite the code to not have the dependencies at the edges of the chunks. Most likely that does not directly work. There was a reason there were dependencies in the original task graph, but understanding how the code would fail if we were to write it to make p chains can enable us to see how the algorithm can be fixed. Or maybe we could realize that there is a particular way of chopping that needs to happen, and the algorithm can be written to take advantage of that way to cut. Or sometimes we need to do things very differently, and there is no rules to what will and what won't work. We need to be creative and change how things are done. If we're introducing a number of processors as a parameter, then we can use it when expressing the complexity of the parallel algorithm and the metrics of the underlying parallel task graph. In general, we need to be careful when we change how the codes are written, that we don't increase significantly the complexity of the code. There are cases where we need to increase the complexity a little, but we need to make sure that we don't increase the complexity to the point where the parallelization won't bring benefits.